This video covers chapter 20, which is inference about a population mean. So what we're going to cover in this chapter is the conditions for inference about a mean, what a t-distribution is, also called a student's t-distribution, and when we're going to want to use a t-distribution instead of a normal distribution, how to conduct a one-sample t-confidence, compute a one-sample t-confidence interval, how to complete a one-sample t-test, how do I'm actually going to skip examples of technology because we use R. We're going to go over matched pairs of T procedures and the robustness of T procedures. So let's get started with conditions for inference about a mean. So here are the conditions that are needed for realistic inference about a population mean. We can regard our data as a simple random sample from a population. This is very important. This is pretty standard. The observations from the population have a normal distribution with a standard deviation mu and a standard deviation sigma. In practice, it is enough that the distribution be symmetric and single-peaked unless the sample is very small, right? We want to typically have a bigger sample, and both mu and sigma are unknown parameters. First, we need to be a little cautious. So the following condition applies to all the inference methods in this text. So the population must be much larger than the sample, say at least 20 times as large as the sample. Our population has to be so much larger than our sample. Previously, we assumed that we knew the population standard deviation sigma, and thus we were able to compute probabilities for our sample mean. But in practice, we really don't know our standard deviation, and because we don't know it, we can estimate our sample standard deviation S, and then we can estimate the sample standard deviation of our mean by taking our standard deviation over our sample size. This quantity is called the standard error of the sample mean, this right here, right? This is our SE, that's standard error. You take S over the square root of N. So when the standard deviation of a statistic is estimated from data, the result is called the standard error of the statistic. Again, just reiterating that this is the formula for standard error. So when were we going to need to use a t-distribution? So when our sampling distribution of our sample mean is close to normal, we can find probabilities involving our X bar mean of our sample by standardizing, right? By finding a standard score, a z-score, we know our sample mean minus mu over sigma over the square root of n. That's how we find a z-score. Then we take this to a z-table. The issue is that when we don't know sigma, we estimate it by the sample standard deviation S. But what happens when we standardize? What are we finding? Because we don't actually know mean, and we're using our sample standard deviation. And because we don't actually know our standard deviation, the new statistic doesn't have a normal distribution, okay? So when we standardize, based on the sample standard deviation S, our statistic has a new distribution, and we're going to call that a t-distribution or a student's t-distribution. And I'll give you a visualization of this in a couple of slides. So the one sample t statistic and the t-distribution. So if I draw a simple random sample of size n from a large population that has a normal distribution with our mean mu and standard deviation sigma, the one sample t statistic, because we don't know our sigma, is going to be t equals x bar minus mu over s over the square root of n. And this is going to have a t-distribution with n minus 1 degrees of freedom. And these degrees of freedom is our sample size minus 1. And this will come in handy when we're using our t-table, much like a z standard score as a z-table. A t-distribution has a t-table. The t-statistic has the same interpretation as any standard statistic. It says how far x bar is from its mean in standard deviation units, except here our standard deviation units are an estimate using our sample standard deviation. There is a different t-distribution for each sample size specified by its degree of freedom. As it gets bigger and bigger, as our degree of freedom gets bigger and bigger, it approaches the natural curve, which is exciting. So when we perform inference about a population mean using a t-distribution, the appropriate degrees of freedom are found by taking one from our sample size, right? And we will write our t-distribution within -1 degrees. So the degrees of freedom as t and -1. So a t-distribution has a different shape than our standard normal curve. It's symmetric with a single peak at 0, and it has much more area in the tails. So let's get a visualization of our normal distribution and our t-distribution. So comparing density curves of this normal curve and t-distribution makes several facts apparent. So here we have in a solid line, that's our normal distribution. That dotted line is our 9 degree of freedom t-distribution. And that T2 has 2 degrees of freedom. So here we have our density curve of our t-distributions. They're similar to our normal curve, but not exactly the same. The variability of the t-distribution is a bit greater than that of our normal distribution. And the t-distributions have more probability in the tails, right? They've got like bigger tails because the tails are above than the normal standard distribution. And this is because substituting the estimate for S for sigma introduces more variation because we don't actually know sigma. As the degrees of freedom increase, our t-density curve approaches the normal distribution. And this happens because S is a more accurate estimate of our standard deviation of our population and causes little extra variation when our sample's large. So for this, we're going to use table C. It's available in your book. You can also look for a t-distribution table to determine our critical values for t-distributions with different degrees of freedom. So how would we use our C table? And then in the next video, we will do some examples. So let's get everything up on the board. Suppose we want to construct a 90% confidence interval with our mean mu and a standard deviation of the normal population based on a simple random sample of size in t. So what t critical we should use? So first off, we need to look at the degrees of freedom, which is n-1, which in this case would be 10-1, which is 9, right? So we're going to want to use this highlighted table. Then we move across and find the entry that corresponds with the 90% confidence level. Remember, this looks like a normal distribution. My 90% confidence level would be 5%, or an area of 0.05 in each tail. So the upper tail probability, it's going to be this row right here. It's also labeled, but that's how you could calculate it, but it is labeled. So we're going to use 1.833. Note that this row right here tells you what you'd use if you were doing a normal distribution or a z-score. See how it differs, how it's a little bit bigger for a z. To calculate a 90% confidence interval, we would have used a score of 1.645. So that's where I'm going to end this video. In the next video, we're going to start to do some examples. And there should be 2 more videos for this chapter.